Today, I'd like to look a little more broadly at the equation, the state equation that we've been working on the whole time so far. The thing we've been doing is we've been ignoring the input u. U is a push that the system is giving. And if you notice here, the equation x dot equals ax plus bu, we've been saying x dot equals ax. That means we've been assuming a u is 0. And of course our output is also y equals cx plus du, and we've been just assuming if we find x we can get y, and that's certainly true. So I'd like to show you that x is partly due to the initial condition, that's like with the pendulum, how you swung it, and it's also partly due how do you push the pendulum. You could be pushing that pendulum at the same time. And so part of the answer is due to the initial position, and part of the answer is due to the continuous push that's happening as you push the pendulum. So we have this input u, you can see on this diagram right here, that actually goes into the system. The diagram doesn't really show the initial conditions, but they're inherent in this integrator we've got in there. And so let's look and see what happens if we solve this using Laplace transforms, something hopefully you learned previously in your experience. So taking the Laplace transform of x dot equals ax plus bu is really pretty simple. We just use the property for derivatives, and you get s times the x of s minus the initial condition x at 0, and that equals a times x of s plus b times u of s. And then you can just do some algebra on that, and you can simplify that down and solve for x, and you'll get si minus a inverse times x of 0 plus si minus a inverse times b u of s. Now notice, if I take this equation and I put x of 0 equal to 0, the output is entirely due to u. And if I put u equal to 0, the output is entirely due to x. And you can see that the output of u due to u and the output due to x is added up, and the actual answer is the superposition of these two. This is something we see on linear systems all the time. It's just a property of linear systems. So we can kind of split it up. That's a handy thing. Now if we take the inverse transform of this equation, we can if we think about it, the inverse transform of si minus a inverse is e to the at. You can see that because we just discussed the 0 input response, and we did it in the time domain, and we got e to the at in times x of 0, so that si minus a inverse must inverse transform to e to the at. It makes sense because the inverse transform of 1 over s plus 2 is e to the minus 2t. So we end up with the 0 input response and the 0 state response in the time domain as well. And lastly, if you remember from before, there were these things called transfer functions. The transfer function is basically a thing that when you multiply the input in the frequency domain, in the Laplace transform domain, by this transfer function, you get the output in the Laplace transform domain. And the transfer function inherently assumes that all the initial conditions were set to 0. So you can see the transfer function over here is c times si minus a inverse b. And that's the transfer function from u being the input and y being the output. Or actually assuming that d is 0, which is usually the case. So I hope this helps you understand the 0 input and the 0 state response. The si minus a inverse is called the resolvent, and e to the at is called the state transition matrix.